Hey, so this video is going to be on solving systems of equations using matrices. So think back to solving systems of equations just generally in the methods you've done substitution or elimination to solve matrices. So you have some examples here that you can go through to try to solve it yourself. Just remind yourself how those work. I'm going to focus more on the matrix version of this. So the first thing I'm going to do is teach you how to do this with equations, and then we'll try to introduce matrices in this. We're going to do something called row echelon form. And this is typically a method used to solve systems that get bigger than 2x2s. So with 3x3s, you can still do substitution and elimination. It gets complicated with 3x3 systems, and then once you get into like 10x10 systems, it's way too complicated to do substitution and elimination. You can probably still do it, but it's going to take a really long time. It's really not worth that effort for it. So what we're going to do is do this row echelon form. And what that means is we're going to try to make this like stair step pattern with leading coefficients of 1. So look at these two systems. They're the same system of equations, but rearranged in a certain way. So in this one, we have xyz, xy, xyz, and it's like all muddled up. In this one, we have xyz, then we just have y and z, and then we just have z. It's like in this way that's like kind of already solved for us, because if I try to solve this system, well, I know z equals 2, which means in that second equation, I can just plug in 2 for z. I'll get y plus 6 equals 5, so y equals -1. And then I can substitute those values in for y and z in the first equation and get x plus 8 equals 9, so x equals 1. So I get this solution pretty quickly if my system is written in this form. Whereas from this form, I'm going to have to do a lot of work to even get to z equals 2 and then y equals -1 and x equals 1. Whereas in this form, I can just start at the bottom step and then move up towards the top to get the rest of the variables in. So that's kind of what we want to get to. The method to make it row echelon form is called Gaussian elimination. So as long as we get equivalent systems, right? So systems are equivalent if they have the same solution set. What we're going to do is take a system and then rewrite it a different way to make sure that our goal is that we want leading coefficients of 1, and we want every new equation line to have one less variable than the line that came before it. So what we can do is we can interchange two equations, so we can switch the spots of them. We can multiply something by a constant that's not 0, so we can scale them up and down. And we can add one equation to another equation. Those are the three things we're allowed to do. So let's look at this system. We have 3x minus 2y equals -1 and x minus y equals 0. So I want to get, my goal is I want it to look like x plus, well, I want x plus something y to equal something. And I don't want any x's in the next one. I just want something y equals something. This is what I want that system to look like. So looking at this already kind of looks like that first step. So I'm going to switch the spots of these so that I have x minus y on the top and 3x minus 2y on the bottom. So that takes care of leading coefficient of 1 on the top equation and nothing, and x and y together. So now the next thing is I need to deal with the second line. On the second line, I don't want any x's. So I'm going to have to get rid of the 3x that's on here. Well, how do I get rid of it? Well, I can take this first equation. Right, so I'm going to leave that alone. But on the second line, I'm going to take this and add the first equation to it, but scale it up. So I want the 3x to go away, so I'm going to multiply everything in that first equation by -3. So now that's going to be -3x, and 3x, those will cancel. -2y minus 3, well, plus 3y would be y. And -1 plus -3 times 0 is still -1. So then I'll get x minus y equals 0 and y equals -1. So that gives me my echelon form. From this, I can solve. I know that y equals 1, -1, and then I substitute -1 in for y in the top equation, and I get x equals -1. It is an overkill method for a 2x2 system like this. You don't have to do this formatting to solve the system. It's very easy to solve the system using substitution and elimination. But I wanted to do it on a small version of this first before we start going into the bigger ones. So now let's do a bigger one. So we have x, y, and z in this. And we want to figure out, this is this equation. We want to figure out how we got from here to the second equation. These are the same systems, right? So we want to know, how did I go from this system into this much simpler system? So let's look at what we need. We want, in this one, we need something x plus something, we want x plus something y plus something z equals something. Then we want y plus something z equals something. And then we want z equals something. So in each of these, we want 1 in front of x, y, and z in each row, and then there can be other numbers over there. So first thing, we already have a 1 in front of x here, so we don't have to do anything to that first row. So we're going to leave that as it is. To the second row and the third row, we need to get rid of the x's because there's no x over here. So we're going to add this first equation into the second and third equations. I have a negative x here, so to get rid of negative x, I just need to add x to it. So I'm going to add this equation. So negative x plus x, 3y minus 2y equals plus 3z plus 0z equals -4 plus 9. So that's me adding first equation to second equation. And then I'm going to add, for this, I need to get rid of 2 x's, which means I need to multiply this by -2. So it's going to be 2x minus 2x minus 5y minus 2 times -2y plus 5z minus 2 times -3 times 3z equals 17 minus 2 times 9. And this is adding -2 times the first equation to the third equation. So I can simplify all of that. I'll get x minus 2y plus 3z equals 9. I didn't do anything to the first equation. To the second equation, I've added the first equation to it. So -x plus x, that gets rid of the x's. 3y minus 2y is just y. And then there's just a 3z. And then -4 plus 9 is 5. On the bottom equation, 2x minus 2x cancels out. Minus 5y plus 4y is minus y. Plus 5z plus 5z minus 6z is minus z. And then 17 minus 18 is minus 1. So now I have the first equation looks correct. It's 1x plus something y plus something z. The second equation also has 1y plus something z, so the second equation also looks correct. So all I have to do is fix the third equation. In the third equation, I need this y to go away. So to do that, I'm not going to touch the first equation. That one has been dealt with. We have it perfect. Second equation, I'm not going to touch it. We have that perfect. The third equation, I'm going to add, I need to get rid of the y, so I'm going to add the second equation to it. So minus z plus 3z and minus 1 plus 5. So I've added the second equation to the third equation. And now I get x minus 2y plus 3z equals 9. Y plus 3z equals 5. And then minus y plus y, those cancel. Minus z plus 3z is 2z equals 4. In the last step, we just want this to be a 1 instead of a 2. So I'll just divide that by 2 on both sides. I get z equals 2. And so then I end up with this equation that looks like what I had up here. Z equals 2, y plus 3z equals 5, x minus 2y plus 3z equals 9. Using these row operations. Then I can go ahead and solve it, right? I can do z equals 2, and then y plus 3 times 2 equals 5, so y equals -1, and then x minus 2 times -1 plus 3 times 2 equals 9, so x also equals x equals +1. So sometimes when you do this, you'll get things like 0 equals 2. If you get something like that, then it's a no solution case. And sometimes you might get something like 0 equals 0, or 5 equals 5, or something that's always true. In that case, then there are infinite solutions. This is a little complicated, right? There's a lot of steps in this. So try to go through it again, slower maybe, and try to do it for yourself and see where all these additions and subtractions are happening. Really, this is just like the substitution method or elimination method. It's like the elimination method, basically, but like scaled up a lot to do this. So I have some practice systems for you to work on. But it's still kind of complicated doing it this way. There's a lot of x's, y's, and z's thrown around, and it makes it really confusing, and there's a lot of things to write down, that it is still not the easiest method to solve it. So this is where matrices come in. We're going to do that same process, but use matrices instead. What we're going to do is use something called an augmented matrix. What the augmented matrix is we're going to take the system, and instead of x, y, and z, we're just going to write the numbers in front of them. We know the place values of them because of where they are, so I'm just going to take like 1, -4, 3. -1, 3, -1. 2, there's no y, so that's going to be a 0, and then -4. What makes this augmented is that I'm also going to add in what they equal on the right. So this is kind of like when we did synthetic division, right? You write all the coefficients down of a polynomial. That's kind of what we're doing here. We're writing all the coefficients down to do the same process as we would algebraically using all those variables, but to write it in a simpler way. The same way synthetic division works. So you're doing the same polynomial division process, but it tends to be quicker and simple because you don't have to write all the x's and x squares and stuff down. Here we won't have to write the x and y and z down. To solve this matrix, we're going to do the same thing we did with the equations, using the same operation. So we can switch around the rows, we can multiply them by something, or we can add some rows to a different row. We want the first entry in the row to be 1, and we want zeros for the columns down the rows. So we want this to look like 1, 0. We want it to be 1, something, something, something. Then we want 0, 0. Then we want 1, something, something, 0. And then 1, something. So what we want it to look like. Right? Just like how we wanted x, something, something, and then no x's, and then no x's or y's. That's what we're doing here. So let's start with this matrix. So we have 1, -4, 3, right? Yeah. -1, 3, -1, and 2, 0, -4, and then 5, -3, 6. So we want to make the first row looks correct. We have 1 in the first entry and then some numbers after it. That's already fine. So we want to get rid of the first column in the other rows to make these 0. So I'm going to add. I'm going to leave this row the same. But I'm going to add the first row to the second. So I do -1 plus 1, 3 minus 4, -1 plus 3, and -3 plus 5. And in the third row, I have a 2. So to get rid of that, I need to add -2 times the first row. So -2 times the first row, -2 times the first row, -2 times the first row. So this is going to be 1, -4, 3, 5, 0, -1, 2, 2, 0, 8, -10, -4. So now we have the zeros on the bottom. Now we need to make the second row a 1. Right now it's a -1. So we're going to change that. Just multiply the second row by a -1. So that becomes a 1, this becomes a -2, this becomes a -2. Next step, we want this to be a 0. So I'm going to have to keep all of this the same. But now I want to get rid of the 8, which means I need to subtract off 8 times the second row. And again, this is still a pretty long, cumbersome process. This is not, like, solving systems of equations is still a difficult thing. What we're just trying to do is find most streamlined processes to solve these. And again, this is like totally supplemental. This is just like extra information. At some point, if you do a linear algebra class, you'll be doing this. But this is just like extra information right now. So you get -10 plus 16, which is 6. And then this will be -4 plus 16, which is 12. The last step here is I need this to be a 1. So I'm going to divide this by 6. And I get that. So at this point, I can convert it back into the system of equations. So this bottom row, that was z. So I know z equals 2. This is y minus 2z equals -2. And x minus 4y plus 3z equals 5. And using this, I can substitute in. And I get y equals 2. And then I can solve for x. And I get x equals 7. So again, that's how you would do this row echelon form to solve systems of equations like this. So you'd have to do these row operations with them, really manipulate all the equations, and then go through making 1s as the first entry as like a diagonal. Like you want this diagonal of 1s, and then everything left of it needs to be 0, and then right of it you can have some numbers. This is your basic version. There's one more thing you can do with this. I'm going to show you that again. It's all supplemental. And obviously I'm just doing one example for now, just for you to know what it is. I'm never going to test you on this. This is just extra information for you. We can also do something called reduced row echelon form. What that means is, see in this problem, we did all this work with the matrices, and then we had to convert it back into equations to solve it. Reduced row echelon form means that we're not even going to have to convert it back into an equation to solve it. We're going to do a little bit more with the matrices to just be able to directly read off the solutions. What we want here is we want a matrix that's going to be 1, 0, 0, right? So the y's and z's are 0. Then here the x and z is 0, and here the x and y is 0, and we just have some numbers there. So we're going to try to make these numbers zeros as well, which is going to take a little bit more row operating that we'll have to do. It's still possible, it's just a few more steps. So let's take what we had at the end. We had 1, -4, 3, 5, 0, 1, -2, -2, and then 0, 0, 1, 2. basically what we're doing in this is we're doing the same thing we would have done with the equations, right? The same process here, but we're doing it with matrices to cut down on how much x's, y's, and z's we have to write. That's all this is trying to create a shortcut for. So at this stage, we have the row echelon form, where it's a diagonal of ones and then zeros to the left of it. And now we want these numbers to also be zeros. So let's work on making zeros on the, well, let's see, what's going to be easiest to make zeros to. Let's try to make the first row zeros. So if we want to get rid of the 4 up here, actually, yeah, it's better to work in columns on this. So we want to make, the first row already has 1, 0, 0. The second column, first column. Second column has a negative 4 in it, so we want to get rid of that. So to get rid of that, we'll do 4 times this 1 on the top there. So 1 plus 4 times 0. The reason we do it this way is because then it doesn't mess up the stuff we have before, because you'd just be adding 0 to it. So this would be negative 4 plus 4 times 1, and then 3 plus 4 times negative 2, and 5 plus 4 times negative 2. This row stays the same for now. This row stays the same for now. And we'll get 1, 0, and then this becomes 3 minus 8 is negative 5. 5 minus 8 is negative 3. And we get this matrix. So now we have the first column looks right. First column looks right. Second column also looks right. We just need to work on the third column. So for the third column, we're going to add the third row to it in different ways. So for the first row, we want to get rid of a negative 5. So we're going to add 5 times this row to it. And again, if we work across the columns, we'll always be adding 0 to the things we already did. So we're not going to mess up things we already finished. So 5 times 1. And then 5 times 2. Then we do 0 plus, on this one, we need to get rid of negative 2. So I'm going to add 2 times the second row. 2 times the third row, sorry. And then keep these numbers the same. And so then we get 1, 0, 0. And negative 3 plus 5 times 2 is 7. And then we'll get 0, 1, 0. Negative 2 plus 4 is 2. And then we'll get 0, 0, 1, 2. And now we can just read these answers off. X equals 7, y equals 2, z equals 2. Which is the same answers we got here. X equals 7, y equals 2, z equals 2. And really all we did was this process with the x, y's, and z's, but we did it in matrices instead. I find this process cumbersome, but also sometimes really calming for me, just because it feels like a puzzle that I'm going through and there's like a set way to do it. So these problems do take time if you do it this way, but it helps you solve systems and it scales up to any size system. I would not do this on a 2x2 system, but like 3x3s, 4x4s is where I'd start using this method to solve it. It would be, I find it more efficient for those bigger systems. For small systems, I think it is way overkill to use this method to solve it. So again, I have some more practice problems that you can try doing these methods on to solve. And again, this is totally supplemental, just extra information if you want to see why matrices can be useful in some algebra stuff.